Right. So I forgot to say this like at the beginning that like this event has been arranged thanks to the funding offered by Sundar. So like I sincerely thank Sundar for like funding this event, and I received a lot of help from Vijay, like Tarunji, the CDIP team. So thanks all. Thank you very much for helping us arrange this event. And now, like I would request like Professor Rohit to introduce the next speaker.
So we are very happy to have Professor Mrinal Kumar from TIFR. So his research interests include a wide range of topics: complexity theory, algebraic complexity, algebraic algorithms, coding theory, and yeah, more generally pseudo randomness. And so some of his recent work was showing this amazing result about closure of formulas under factorizations. So before TIFR, he was in Rutgers for his PhD, also at Harvard University, and then he was also here. And yeah, it's always nice to have nice to have him back here. And we have some small token of appreciation.
Oh wow!
Yeah.
Yeah. Okay. Thank you. Okay. I'm audible to everyone, right? So I'm going to talk about this this very nice old paper by on the construction of unbalanced expanders. So I'll tell you what unbalanced expanders are. You would have seen expanders as a part of the course. We'll talk about what unbalanced expanders are. I'll tell you what explicit means. But let me tell you the references. So the original paper is by Guruswamy, Omans and Vadan. This would be around 2009. But the proof we are going to do is from a more recent paper of Kalev and Tashma. It's basically the same idea, but implemented in a way that's more self-contained, requires less background, and the proof is almost completely doable in whatever 90 minutes. I'll define everything. I don't know what the background is. Okay, so the setting is the following. So we are going to be looking at bipartite graphs. There are n vertices on the right, on the left, m vertices on the right, and the graph is left regular. And d is the degree. These are the three parameters that we'll largely work with. You should think of this as in the setting where the left side is much larger than the right side. So you're compressing. So m is less than n. Okay, and we say that a graph like this, so G. So G is a comma k expander if for all subsets on the left hand side of size at most k, let's say size equal to k for this discussion, so we are looking at sets here. So this is a set S of size at most a, and we want all such sets to expand, meaning the number of neighbors this set sees on the right hand side should not be very small. How big can it be? If you have a set S of size k, the graph is d regular. How many neighbors can you see? You can see at most d times the size of S. So let's say less than equal to k. The neighborhood of we'll use gamma for neighborhoods. So gamma S is large. So how large? Well, the largest it can be is the size of S times D. But we'll live with something that looks like 1 minus epsilon times S. So maybe I put an epsilon here. So these are bipartite graphs where the right hand side is much smaller than the left hand side. And every small enough set on the left hand side expands. The number of neighbors is as large as you could hope for. It's a d-regular graph. The largest you could hope for would be size of S times D. But what you get is 99% of that. What is A? Good. I could have said so maybe I should say this is A times K or something. A times size of S. So we don't need 3 parameters, 2 is enough. And you should really think of A as being 1 minus epsilon times D. So it's an A comma K expander if every subset of vertices on the left hand side of size at most K has A times the size of the set many neighbors. And the kind of regime of parameters we are going to be interested in, this A is going to be as large as possible. So it can be at most D, but it's going to be 99.99 times D. Think of epsilon as a tiny constant, 0.0001, something fixed for the discussion. Is it clear what an unbalanced expander is? Why is it unbalanced? It's unbalanced because the right hand side is smaller than the left hand side. That's why we call it unbalanced. This is not your typical expander, right? I'm guessing that a typical expander, have they seen bipartite expanders in the course or no? But right, so but you can take your whatever expanders you have seen in the course and make a bipartite graph out of it with expansion properties. But there you will see that the left hand side and the right hand side are of the same size. You look at the double cover of the graph. So yeah, so what makes this problem different are 2 aspects. One is that it's unbalanced. We want to construct graphs where the right hand side is smaller. Because the right hand side is smaller, it makes it harder to get this property. So that's one part, and the other is the fact that we want the expansion to be as large as possible. We want A to be 1 minus epsilon D. So these are the 2 things that make it this problem a little bit different than the kind of questions you have already seen.
This connection with that follows. So you have given its definition to expand. Temporary is not even clear if such a fixed.
Right, great. So I will tell you that they exist. Okay, so are we good with the definition? This is the most important definition in today's discussion. So if there are questions here, please ask now. Okay, good. So do they even exist? So they do exist. I'll tell you with what parameters. Sorry? Epsilon is fixed for this discussion. Epsilon is 0.00001. Let's not have too many parameters. Right. Right. So you would see that you cannot get beyond epsilon being half for that. Those constructions will stop at epsilon being half. Epsilon being close to 0 is what makes this problem different. So you can get epsilon half, you can get both sides balanced by all these spectral constructions, like LPS based constructions will give you that. What we want is something different. So it's not known how to get this kind of a parameter regime, or it wasn't known at the time, at least from spectral methods. I think it's still not known how to get these things out of spectral techniques. Okay, so let me write what is known. So for every epsilon greater than 0, so there exist graphs. So that sort of graphs, G with N, M, let's say D, with D being So let's set, there are too many moving parts here. So let's set some numbers. So let's pick m to be n to the 0.99. So we are just compressing. The left hand side is polynomially smaller than the right hand side. So in this setting, and epsilon is some constant. So epsilon can be an arbitrary constant greater than 0. In this case, you get d to be order log n over epsilon, and you get a to be 1 minus epsilon times d. This is what we wanted. Actually, we should turn this around and ask what k do you get out of this. So maybe the right way to write this is so k is going to be about epsilon m over d. So sets of size roughly this expand. We cannot expect expansion from sets of size bigger than m over d because there's not enough room to expand. If you pick a set of size m over d larger than m over d, then the number of neighbors is greater than m. Right? D times that size of the set is greater than m, so it can't expand. So we can't expect k to be more than m over d. What you get is epsilon times m over d. Yeah. A complete graph will have this property. Getting d small is the point. The degree of a complete graph will be m. So d must be m. What you are getting here is d is logarithmic in those norms. Yeah.
Is this tight? Like you can't do better?
Good. It is known to be tight in some settings of parameters, but there are a lot of moving parts here. So what tightness means needs some quantification. I am not going to do that. So in some sense, it is tight. We know, and those results are also very non-trivial, that you are very close to the best. These constructions are the best we can do essentially, but I won't say more. Is that okay? So this should set us. This should give us the sort of the ultimate ballpark of parameters to look for. What we would like is the right hand side to be polynomially smaller than the left hand side. We would like the degree to be logarithmic in the size of the number of vertices, and we would like sets of size roughly m over d to expand. That's the range of parameters to shoot for. Great. So these expanders, so the paper GUV, they study these expanders. So the paper constructs a whole bunch of pseudo-random objects. They construct things called extractors. So their eventual goal was to construct extractors, and extractors up till then were very hard to construct. So these are graphs with some more pseudo-random properties. What they showed was this construction of unbalanced expanders was the first step in their eventual construction of extractors. So they used this and along with some other machinery to combine them together to get the best extractors. I think that we know in some range of parameters. So that was one application. The other application of unbalanced expanders that I think we know from the late 90s was for data structures for set membership. So here the problem is that you have a universe of size n, and you want to store a set of size k such that I can answer membership queries very fast. So your data is a set of size k of a universe of size n. So you get to pre-process the data, store something in the memory, and then I'm going to give you an element and ask, does this element belong to the set that you have stored? And there are two parameters to optimize here. One is the query the number of accesses to the memory every time I ask you a query, and the other is the amount of space you are using. And it was known from the late 90s that we can construct surprisingly good data structures for set membership if we had explicit construction of these graphs. But the data structure construction was okay even with randomized things, even when you could show that there exist good data structures. But explicit construction of expanders, unbalanced expanders, gives you explicit construction of data structures for set membership. But I'll not talk about any of the applications. I'll just talk about an explicit construction of these graphs with very impressive parameters. They won't exactly match that. But questions? Good. So let me write the main theorem. I'm going to write a parameter light version of it, which is what we are going to work with. Okay, let's parse it. Let's parse the statement. So we are going to construct explicit graphs. So these are graphs which we will construct in polynomial time in the parameters. That's what explicit means for this discussion. And these are graphs where we can, if you tell me a neighbor on the left, a vertex on the left, I can find its neighborhood on the right very, very fast. In polynomial time, in the description of the vertex, and so not even in poly n time, actually in poly log n, comma log d time. Okay, so for now, explicit mentally, if you haven't seen this word before, it should just mean you can construct the graph in polynomial time. The theorem will prove something much stronger. Let's not worry about that. So we are going to construct a graph. So how are we going to do it? So we'll pick a prime p, pick numbers s and n such that s is smaller than n is smaller than p. Let's forget about the plus 2's here. The left hand side will have p to the n vertices. The right hand side will have p to the s vertices roughly, s plus 2. The degree is going to be p, and this is going to be an a comma k expander with a being this. So how do we make sense of this a? So one way to make sense of this a is that you set k to be something small enough such that this part looks like epsilon p. Okay, so pick k to be such that ns over 2 times p times k to the 1 of s plus 2. It's like epsilon p. So if you pick k, let's say at most epsilon p, so then k is going to be something like p to the s plus 1 times some poly in ns factors. So that's the bound on k. So if you take k to be that, then a is going to be 1 minus epsilon p. The degree was p, so 1 minus epsilon p is 1 minus epsilon times the degree of the graph, degree of the vertices on the left hand side. So we are getting what we promised, at least in this parameter. Okay, is that good? So we can quickly see what k this gives. So this says k is less than p to the s plus 1 times epsilon to the s plus 2 divided by s by 2 to the, okay, whatever, something. So as long as k is smaller than this, what you're getting is almost full expansion. You're getting 1 minus epsilon times d neighbors times d times the size of the set neighbors for sets of size at most this.
Just to confirm, k is of that order, right? Epsilon.
It is still of that order. Notice that it's still of that order. M was p to the s plus 2, d is p. So m over d is p to the s plus 1. There are some constants here, but it is of that. Is that good? These are good parameters to be had. All right. Now we can set parameters in a way that will make it look like this, but will not do that. I will invariably make a mistake doing that. I don't want to do that. No, I'm saying, yeah, I'm saying k, as long as k is smaller than this, you will get expansion. Yeah, so. Okay. Questions? So that's the theorem. For the remaining 1 hour or so, we'll try to prove that theorem. I am ignoring the epsilon powers here. I don't think even with the right fitting of parameters, it will not match it. There will be poly epsilon gaps everywhere, but I am not sure.
Because m and n are kind of connected.
Right.
Just comparing with this, if I want m which is square root n, that will also fix my d.
Right. It will, yeah. There's a whole bunch of, yeah. So one suboptimal range of parameters, and that's how I think of it, is of this construction, is when you think of p to be growing and think of n and s as both constants. It doesn't give you that bound because the degree is p, which is sub-polynomial now. It's not logarithmic, but it's still very impressive in that way. But in order to get closer to that, and the paper does that, it will set p to be, I think, a constant, and n will grow and s will grow slowly compared to n, and you get something. Or sorry, it will set p to be logarithmic, and then. But okay, I think I really think we shouldn't get bogged down in the parameters here. That's not the that makes the result impressive, but there are really neat ideas here that are interesting, even if this gave the worst expander of all time. Questions? So is the definition clear and the statement clear and what we are aiming for? Okay, good. So let's try and prove that now. So the graph is going to be quite easy to describe. I can describe it immediately. And then it will take us some time to prove that it indeed has the properties that we claim. So here's the construction. Okay, so I'll need one or two things, some algebraic facts that I will recall here. Okay, so we are going to be working with the finite field Fp. What does this mean? This means, so this is a number system, it's a field where our numbers are 0, 1, 2 up to p minus 1. And we are doing all arithmetic modulo p. So if p is a prime, this has all the properties that we expect from things like rational numbers or real numbers or complex numbers. What kind of properties? Well, addition and multiplication behave the way you expect. They are commutative, associative, things distribute the way we want them to distribute. But also some algebraic properties hold true. So, so specifically a low degree polynomial does not have too many zeros. I'll state the precise fact we need in a little bit. But if you take a degree d polynomial that's non-zero over rational numbers, the number of zeros it would have is at most d. The number of distinct zeros is going to be at most d. The same fact holds if you do arithmetic modulo p, when p is a prime. This fact doesn't hold if p is not a prime. If you are working over modulo composite numbers, then you can have low degree polynomials with many more zeros than their degree. So p being a prime is important for these things. That's the notation I'm going to use for Fp. Okay. Great. So here's the construction. So we are going to identify the set N. This is the set of vertices on the left hand side with the following set. We'll identify the set of vertices on the left hand side with the set of all polynomials. So these are univariate polynomials. X is the formal variable. But these polynomials, the coefficients are going to come from Fp. The coefficients are going to be 0 and up to p minus 1. And the degree is going to be smaller than n. So the left hand side, I said there that the left hand side is p to the n, n is p to the n. Notice that the number of polynomials of degree less than n with coefficients in Fp is exactly p to the n. Okay, so it makes sense. Yeah. Oh, that's magic. So I can't motivate it. It's a construction. I will give you a construction. This is a construction, and it really came out of the blue. And we know that there are connections between these pseudo-random objects, but this is still, even with that context, this is a magic trick. So that's going to be the set N. Now, so a vertex on the left hand side is a polynomial. Your vertex is some f of x. I have to tell you what its neighbors look like. The construction should give you a hint. I said d is equal to p. The number of neighbors, the degree of a vertex is d, and d is equal to p. Right, but evaluations themselves would have given you elements in p, but the right hand side looks like p to the s plus 2. So it's not just evaluation, there's more. So there are This guy has p neighbors and we are going to label them by elements of fp. So 0, 1 up to p minus 1. Let me tell you what the edge labeled by alpha is. The edge labeled by alpha goes to a vertex on the right hand side, which looks like alpha, f of alpha, the first derivative of f evaluated at alpha, the second derivative of f evaluated at alpha, and so on, up to the sth derivative of f evaluated at alpha. So polynomial is attached, the neighborhood store information of the evaluation of the polynomial and all its derivatives up to order s on all points of fp. Okay. This should also tell you what right hand side should we expect. Each of these guys is an s plus 2 tuple with where every coordinate is from fp. So this should, this is m, which is p to the s plus 2. Yeah. Good. I will say something on it, but not a lot. Yes, Ajit, you had a question.
This alpha is an integer from 0 to p minus 1.
Oh, alpha is a field element. We are identifying the field element. We are thinking of them as integers from 0 to p minus 1.
It is modulo.
Yeah, all the arithmetic, all the evaluation is modulo p. There was a question here about are derivatives well defined? I'm guessing the question is because your typical definition of derivatives involves limits. Okay, it's being recorded. Otherwise, I have more to say on this. Yes, derivatives are defined. There is a right notion of derivatives, which we should have defined in the first place before going to the limit-based definition. But there is a way of formally defining derivatives, which makes sense. Okay, and what is the formal definition of a derivative? Well, the derivative of x to the m is m times x to the m minus 1. The derivative with respect to x of any field element is 0, and then you linearly extend this. So that's formal definition of derivatives. It doesn't require you to compute limits in any, which don't make sense over finite fields. Is that okay? Is the graph okay? The left hand side is labeled by polynomials of degree at most n with coefficients in fp. The right hand side is labeled by s plus 2 dimensional tuples over fp. And the connections, so the edges are going to be labeled by field elements. So you take a vertex, look at an edge labeled by the field element alpha. It's going to take you to the s plus 2 tuple on the right that stores alpha, f of alpha, the derivative of f evaluated at alpha, second derivative, and so on up to sth order derivative. Are we good? Is the definition of the graph clear? So all the syntactic properties should be easy to see now. The left hand side is indeed p to the n, the right hand side is indeed p to the s plus 2, and the degree is indeed d. We have to show that for all small enough sets, you get nearly optimal expansion. No, it's exactly equal to p to the n. So you are looking at polynomials of degree less than n. So which means degree at most n minus 1. So a polynomial of degree at most n minus 1 has n coefficients. So it's exactly p to the n. Are we good? Okay. So let me just write m here. So m is we identify it with fp to the s plus 2. Okay. Okay, so now we have to show something. We have to show that if we pick sets of size roughly p to the s plus 1 on the left, the number of their neighbors on the right is 1 minus epsilon times p times the size of the set. Okay, so before going further, so I want to elaborate on the fact that I had stated. So let me first write that formally. Here's fact 1. So let's say g of x, let's be a join x, is a non-zero polynomial of degree d, then the number of zeros of G is upper bounded by D. Okay, but something stronger is true. What is true is that the number of zeros of G counted with multiplicities is at most T. So let me say what that means. So we say that an alpha is a zero of G of multiplicity K we are using, so let's say T, if for all I less than or all I in 0, 1 up to T minus 1, the ith derivative of T evaluated at alpha is 0. So not only does the polynomial evaluate to 0, all its derivatives up to order T minus 1 continue to evaluate to 0. That's what a 0 of multiplicity T is. And a generalization of this fact is true when we count zeros with multiplicity. So this is fact 2. So suppose you have a g of x and fp adjoint x non-zero, degree d, then so let me write this. So sum over alpha in fp, the multiplicity of g at alpha is at most t. So just something that's a 0 is a 0 of multiplicity 1. Notice this counting starts from 0 and ends at t minus 1. So if you stop at 0, then you get a multiplicity 1 root. So now go through all the alphas, count things with multiplicity, with their right multiplicity, and what you get is going to be at most t. We can make it an equality if we start counting in the closure of FP. Yeah. Well, I mean, it's like when we are writing this statement over rational numbers, we only get an inequality. But when you start writing this statement over complex numbers, you get an equality. So the same thing. Go to the algebraic closure, you get equality. Okay. Good. We aren't going to use it in any in a very strong way, but this construction comes from the construction of error correcting codes called multiplicity codes. So these are codes that where we identify the message space with a space of polynomials of some degree, and the encoding of this message is going to give us evaluations of this polynomial and all its derivatives up to some order s at all points over fp. And we can use that fact to show that this forms a code with good distance, very good properties. And we now understand that these codes are also have decoding properties that make them very, very special. So that part of the reason why, so I had written the names of two papers there. So Kalev and Tashma's paper, which is a couple of years old, and Guruswamy Uman Swadan, which is older. So Guruswamy Uman Swadan did not give this construction. They gave a similar construction, but that was based on not multiplicity codes, but something called folded Reed-Solomon codes. These were codes that had just been discovered by Goswami and Rudra just a couple of years before that paper, and they were shown to have very good decoding properties in some regime of parameters, and the GUV construction of expanders was based on that. Kalev and Tashma, so in the gap between the GUV paper came out and the KT paper came out, our understanding of multiplicity codes also was advanced significantly. And by the late, so by 2020, we knew that multiplicity codes have amazing list decoding properties, amazing decoding properties in some regime. And Kalev and Tashma noticed that you can take the high level picture of the GUV construction and remove the code that they were using, and you can base the construction on these codes and get cleaner proofs out of that. So with similar parameters, you don't suffer too much of a loss in parameters. So we will indeed see this proof. This proof is from Kalev and Tashma's paper. Okay. Questions? So we are done with the description. Now we have to see the proof. Okay. Yeah.
Like, just as a side question, then can this be generalized to like arbitrary code? Like you give me certain properties of a code and I'll say yes, it will form an expansion.
Right. So yes. So you can generalize it somewhat. I mean, there are theorems connecting what are called list decoding properties of codes with various pseudorandom objects, including expanders, extractors, pseudorandom generators, all sorts of things. This proof is not. I mean, this proof is still not going to be black box. It's going to the proof will mirror some of the decoding algorithms, but it's not the kind of statement where you say, oh, if this code satisfies these properties, and these properties are very clean and natural, then it will satisfy. Somehow it's there's some disparity in the range of parameters that we need to work in for constructing some of these objects, and the range of parameters that's typically studied in coding theory. But yes, but there are some connections, and these connections do sometimes give us interesting things. But often you have to go, I mean, you have to take a construction of a code and go and do stuff before you conclude that it actually gives you an interesting pseudorandom object. But that's a good place to start. Okay, questions? Okay, good. So now we'll try and prove the theorem, and we'll be able to see most of the proof. So what do we need to show? So here's the main technical claim. Actually, we need some notation before we can state the claim. So what is it that we need to show? So we have to show that, so remember the picture was this. This is basically fp to the n, this is fp to the s plus 2. And we have to show that every small enough set here expands. So we have to pick small enough sets and look at their neighborhood. We want to say that this is larger than this. So this is, so let's pick such a set W. So W is a subset of fp to the s plus 2. And we want to look at the set of polynomials, set of vertices on the left such that their entire neighborhood is contained inside W. So let's define this, let's call it the list of W to be the set of vertices on the left such that their entire neighborhood is contained inside W. In this description, we can write this as the set of polynomials we adjoin x, degree less than n, such that for every alpha in Fp, alpha, f of alpha, 1 of alpha, s of alpha is contained in W. These are all polynomials such that, polynomials on the left such that all of their edges lands them inside the set W. W is a set of points on the right. Yeah. It's some arbitrary set. Yeah. We will put that, but right now for this definition we don't need anything. So W is some set on the right. List of W is the set of polynomials such that their entire neighborhood lives inside W. In order to show, so our goal is to show that every small enough set on the left hand side expands. The way we are going to show this is by picking sets, small sets on the right hand side and showing that their list has to be small. Okay, so the main claim will be that for all W, subset of Fp to the s plus 2, size of W being less than 1 minus epsilon times P times K, list of W, the size of list of W is less than K. So this is showing that sets of size k expand. Is that good? We are going to prove the contrapositive. So we'll, so if, so this is showing that the size of, so this is showing that sets of size k must expand. Okay, so far so good. So I want to keep something. Again, erase the left hand side.
How much stronger is the condition as the spectral?
How much?
Stronger. It's not equivalent. It is. It implies expansion, but
Right.
how much stronger is it?
So, sorry, equivalence to what?
Expansion.
To expanding from the left. Oh, we want almost optimal expansion of sets of size k. So
We say expansion from the left is not equivalent to this claim.
expansion from the left of sets of size k is equivalent to this claim. Expansion of sets of size k is equivalent. Expansion, where by expansion you mean 1 minus epsilon times, that's equivalent to this claim. It's the contrapositive of the same claim. We want to show that every set of size k has at least 1 minus epsilon pk neighbors. What we are trying to show is that if you pick a set of size less than 1 minus epsilon pk on the right, its neighborhood on the left is less than k.
So I mean, like, I guess to phrase that question differently. So the question is that, like, you wanted to argue that for any subset on the left of size no larger than k.
Right, good.
That has,
Yeah, let's make it equal to k. You prove it for, what we will prove will be a little bit stronger, but this is cleaner to write. So I'll stick to this. Yeah. But Raghu, you okay? Yeah. Okay. Good. So now the hard part. I mean, the hard part. So we'll prove this claim. The proof will be completely elementary and self-contained. But it's a difficult proof to motivate without sufficient context. So many of the ideas that will go into the proof actually came out of coding theory, algebraic coding theory, where ideas like this have been used at least in the modern literature since the 90s. And if you expand your funnel a little bit, since the early 1900s to prove theorems in math and in CS. So these are proofs that are based on the so-called polynomial method. We will see why it's called the polynomial method. But let me tell you what the main steps are. So the proof will be in 3 steps. Step 1, we'll call this the interpolation step. What we are going to do here is, so we have a set W, right? The setting of the claim is very clear. We have a graph defined and we have a set W of size less than 1 minus epsilon pk. And we want to understand the list of this set, the set of vertices on the left such that their entire neighborhood is contained inside W. In the first step, we will go from looking at this set of points as a set of points to looking at a multivariate polynomial with some properties. Okay, so the interpolation step, what we are going to do is we'll find a non-zero, low degree. So I'll have to elaborate on what this means. Polynomial Q has s plus 2 variables. So it's let me label the variables suggestively. So let's call it x, y0, y1 up to ys, such that for every alpha comma beta naught up to beta s in W. Remember, the points in W are S plus 2 tuples, and because of the way we had defined things, the first coordinate and the remaining coordinates are a little bit different, so we'll use this notation to distinguish them. Q of alpha comma beta naught beta 1 up to beta S is 0. So we have a set W. We are going to stop working with the set W, and we are going to think of the set as points in the 0 set of a low degree polynomial. We'll get our hands on a polynomial Q on S plus 2 variables that vanishes everywhere on the set W, and we would want this to be low degree. I'll come to what low degree is here. That's going to be the first step. So we'll show that there is a polynomial of this kind. The second step is going to be to show that the list of W is somehow related to this polynomial. The list of W has something to do with this polynomial. So informally, we'll show that every F in list of W is contained in the belly of Q. Okay, so formally, we'll show that for every F in list of W, Q of X comma F of X comma the first derivative of F, so on, S of X, this is 0. So we'll show that if you restrict the variables y0 up to ys, if you restrict the variable yi by replacing it with the ith derivative of f for any f in the list, you're going to get 0. Okay, so Q contains all the information about all the polynomials in the list in this very specific form. And step 3 is that we will use W and star to conclude to upper bound. It depends on what degree is, but yes, it's almost direct. Yeah. So to upper bound, doesn't step 2 follow immediately from step 1? It is. Okay, so eventually we'll use W and this property to conclude that the size of the list is not too large. Okay. If you have seen decoding algorithms for any of these codes, you'd notice that they also look like this. There are 3 main steps and they actually look like this. The difference is, the main difference to me is here in the third step, where when we are asking something very strong, we want almost complete expansion. So we need really, really good bounds on the list of W. Typical list decoding algorithms for even multiplicity codes do not give you such good bounds. So we don't care about such good bounds in that case. But otherwise, this sketch should look like any of the decoding algorithms for many of the algebraic codes. They have the same structure. So these ideas are traced to that.
This list is that list.
This is list is that list. Yeah. So if you are familiar with the context, the setting we are in, this is the setting of 0 error list recovery. It's not list decoding because the set W for the same alpha contains many extensions, many betas. So it's not list decoding, it's list recovery, and it's 0 error list recovery because we want the entire neighborhood to be contained in W, not 99% of the neighborhoods. There is a list of polynomials that shows up when you design list decoding algorithms or list recovery algorithms, and I think that's what you mean. Okay, but ignore that. Okay, so this is what we are going to prove. Okay, I will rewrite the claim up top. Okay, good. So let's start with this. So we have a set W. We need to find a polynomial on S plus 2 variables such that it vanishes on all the points in the set W. Okay, If you have seen it, you have seen it. If you haven't seen it, let me just tell you how to do it. So we have to find a polynomial q. So q is q of x comma y. Let me write it like this. So x y. This is a polynomial. It's of the form. It has some monomials. So it's of the form sum over some e. Or let's say I comma e. Q sub I comma e times x to the I times y to the e. This is this e is e1, e2, e0, e1 up to es, and this is so y bar to the e bar is y0 to the e0, y1 to the e1, ys to the es. I'm writing it slightly succinctly. So we have to find a polynomial. So polynomial is of this form. The degree has to be bounded, which means we should look at vectors. We should sum over things where I and E are not too large. So we'll make it precise. But what is this condition? This condition says that for every point in W, Q must evaluate to 0 at that point. So yeah. Right, that would be the standard notion of degree. We will have to work with something slightly different. I will come to it. But yes, that's a good thing to keep in mind. So we want the constraint on what we want from Q is that for all alpha beta in W, Q of alpha beta is 0. But this is the same as in this language. This is the same as saying sum over I comma E. Q sub I comma E, alpha to the I, beta bar to the E bar is 0. We want this for every alpha beta in W. So we want QIEs to satisfy this for every alpha beta in W. Notice that if you view these conditions as functions on alpha beta, what you are imposing is homogeneous linear constraints on QIEs. So you could have written this as this is a linear system where this depends on alpha beta, so this depends on the set W, the matrix, and we are multiplying it by the coefficient vector of Q. And we want the vector to be in the kernel of this matrix. Okay, so our goal because of future applications of this Q is to find such a Q where the degrees are low. So how do we do this? So we have to argue, clearly if you set all the QIs to 0, this is clearly a solution. So the all zeros vector is clearly a solution, but I want a non-zero solution. How do you ensure that a homogeneous linear system has a non-zero solution? Right, there should be some rank deficit. So if you can ensure that the number of variables is larger than the number of constraints you are imposing, the solution space will have dimension at least 1, so you will get a non-zero solution. So we want the number of coefficients in Q to be larger than the number of constraints we are imposing. So we want the number of coefficients in Q. I have not, I will soon. So number of coefficients, we want this to be larger than the size of W. So these two requirements are in tension with each other. We want Q to be low degree. Low degree forces us to only look at certain coefficients. Wanting this system to have a non-zero solution requires us to have sufficiently many coefficients so that the number of coefficients is more than the number of constraints. So these are requirements in tension with each other. So the parameters have to be set in a way that this condition holds. Right? We will not do it right now. We will do it soon. But this is what we want. Let's understand where the low degreeness shows up and how we use it. That will let us specify the summation. So I'll erase this. No, I want to keep that part. So let's look at, suppose we somehow manage to get our hands on such a Q. Let's see how step 2 works. Raghuvan said it's immediate, which it is. But let's spell it out, and that will give us some insights into how to impose constraints on Q. So what do we want from step 2? We want to show that for every f in the list, if we plug in, if we replace the variable yi by the ith derivative of f, what you get is 0. So let's pick an arbitrary f in list of w, and let's define the polynomial r sub f of x, which is q of x comma f of x comma the derivative and so on. Our goal is to show that r sub f of x is identically 0. It's the 0 polynomial. Why is that true? And when is that true? What do we need for this? So something that will be sufficient is that, so observation is that for every alpha in Fp, r sub f of alpha is 0. Is that clear? For every alpha in Fp, the claim is that r sub f evaluates to 0 at alpha. Why is that true? So let's see what r sub f of alpha is. R sub f of alpha, this was the definition, so we plug in alpha here. So you get q of alpha, f of alpha, the first derivative at alpha, and so on, the sth derivative at alpha. And I want to say that this must be 0. Why is this 0? We haven't used the fact that f is in the list, we have to use it somewhere, right? So why is this 0? The reason this is 0 is because since f is in the list, the alpha neighbor of f, all the neighborhood of f was contained in the set W. In particular, the edge going from f with label alpha was going to this vertex precisely. And when we constructed the polynomial q, we imposed the constraint that for every vertex in W, every label in W, q vanishes at that vertex label. So this is 0 because this is contained in W. That was a definition of f being in the list of W. Is that good? If that's not clear, now is a good time to stop.
Maybe someone might want to see the definition of list again.
I raised it. Okay. Remember what list of W was? This was the set of all polynomials f of x in Fp adjoint x, degree less than n, such that for all alpha in Fp, alpha comma f of alpha comma the derivative at alpha and so on belongs to W. So in the graph, these are all vertices on the left such that their entire neighborhood is contained in the set W. So the claim here is that, what we intend to show is that r sub f is 0 for every f in the list. That's what step 2 is asking us to show. The observation we made is that for every alpha in Fp, r sub f of alpha must actually be 0. R sub f evaluates to 0 at alpha. Okay. Is that clear so far? When would this condition imply this condition? When would this imply that r sub f must be identically 0? I want to say that this observation will imply this in certain settings, and we want to set things so that we are in that setting. So when would r sub f, we have the property that r sub f is 0 at all alphas in Fp. We want to conclude from this that r sub f must be identically 0, must be the 0 polynomial. When would that happen? Right. So the second observation is that if the degree of r sub f is greater than is less than p, then r sub f must be identically 0, must be the 0 polynomial. So if the bound on the degree of r sub f was something less than p, then we are done. what is the degree of what is the bound on the degree of R sub f based on the degree of Q? Intuitively, if Q was low degree, R sub f would be low degree, right? But we have to be careful. I mean, what we did was we took Q and we plugged in, we went to the variable yi and replaced it by a polynomial of some degree. So, so in some sense y, the variable y which counted as degree 1 is replaced by a higher degree polynomial in x. So, there is some blow up in degree, there is some weights. So, this is, I mean, this is what we want to ensure. So, we want to find a Q whose degree is low enough such that when we do this replacement of taking the variable yi and replacing it by the ith derivative of f, what we get eventually ends up having degree less than p. That is what we want from Q. Okay, so this low degree condition is going to be ensured with that application in mind. So let me now say what Q is, what the degree of Q is. Okay, so we want Q to look like sum over I comma E, Q I E, x to the I, y to the E. Let us write it explicitly. So, y0 to the E0 to ys to the Es. Okay, and we want, so consider the set, let's say T, it's going to be a subset of natural numbers to the s plus 2, defined as follows. So T is so u comma v naught to vs such that u comma v naught up to vs are all non-negative, and u plus n minus 1 times v naught plus n minus 2 times v1 so on plus n minus s plus 1 n minus s minus 1 times vs is less than 2. I am defining I am defining the set of monomials we want here, defining the indices we want, and so I want to say that we are only going to sum over things in T sub D. Let's not use D, D we all call it delta. And what is T sub delta? It's the sum of two, it's the set of tuples like this where everything is non-negative integer, and the first element plus n minus 1 times the second element plus n minus 2 times the third element and so on, that sums up to less than delta. You could do that, and I think it will be okay. We won't get the same theorem, same result, but we'll get some small variations, I think. The question was, do we really need to make this n minus 1, n minus 2 and so on? We could have made everything n minus 1, and I think that's okay. In the list decoding setting, that's what I would do, and I think it will work here also, but I haven't checked the calculations. Is that okay? This should look natural because what are we really doing? If you take a Q with this property that all the vectors, I mean these are I comma I's where I comma I is in T delta, when we do this substitution that we are doing here, we are replacing the variable y1 by y0 by a polynomial of degree n minus 1, y1 by a polynomial of degree n minus 2. The degree of this is 1 less than the degree of whatever f was, and so on and so forth. The total degree we are going to get will actually be upper bounded by this summation. So it's going to be at most delta. Is that okay? That's what motivates the definition of the set of monomials that Q is supported on. Okay, so now with that definition, this condition will just hold. We will set delta to be something like epsilon p.
Just to like
Yeah.
repeat for my comfort. I mean, the like reason you introduced it is so that I can mimic the structure of RF.
Right, exactly. We want to mimic. Eventually, we want the degree of RF to be small. For the degree of RF to be small, we need to have some guarantees on the kind of monomials Q is supported on. This tells us exactly what monomials on Q are okay for us. And then we set delta to be epsilon times p. But remember, I mean, we need the number of coefficients to be larger than the size of W. I am not going to do this calculation, but it just works out. If you set delta to be epsilon p, the remaining calculations work out. You do indeed, if you count the number of monomials, you do indeed satisfy this constraint.
So why are you not taking delta equal to p minus 1?
Good.
Okay, repeat the question.
Why are we not taking delta to be p minus 1? We need some gap. So in step 3, we will use the fact that the degree is not very close to p, it's a little bit away. The question was why are we trying to save anything here? For this observation, we need the degree of RF to be just less than p. So let's set delta to be p minus 1. It will give us more room to satisfy this constraint. So, but we will need it later in the third step. Okay, so this completes the description of the first 2 steps. So we did it upside down, but let's go back and understand what we did. We picked the parameter delta, we set it to epsilon p. That's the first thing we did. Then we said, well, let's look at vectors of this form with this property. Let's look at the set t sub delta and calculate the size of t sub delta. The size of t sub delta just happens to be larger than the size of W for the range of parameters we are in. That ensures that Q of xy has at least the size of W plus 1 many monomials that it's supported on. And we are imposing size of W many homogeneous linear constraints on these coefficients. So there must be a non-zero solution. Pick one such non-zero solution, work with it. So we picked that non-zero solution, we came to this step, we constructed this polynomial for some f in the list of W. We noticed that the degree of this univariate can be no larger than delta because of how things were set up. And we also observed that because f is in the list, R sub f of alpha will be 0 for every alpha in Fp. So R sub f, which is a polynomial of degree strictly less than p, has p zeros. So it must be identically 0. So Q is identically 0. Q becomes identically 0 when we replace the variable yi by f to the I for any f in the list. So this Q contains all the polynomials f in the list in this form. It has all of them contained inside it. Okay, so now the last step. Questions so far? Yes.
Where will we get the dependence on the other one K from? Like this statement will hold
Right.
for all sets such that W is smaller than 1 minus epsilon times Pk, right?
Right.
So where does the K come?
It will come up. I mean, when you try to do this calculation, remember K was also in the theorem, we stated it as A comma K expander with A being something, P minus something that depends on K.
Right, no, but I was just trying to wonder whether if we choose the delta to be P minus 1, then we'll sacrifice on K somewhere down the line.
We will get a weaker statement here. We will not get what we want to prove here.
Yeah, we get it for a lower K maybe.
You will also lose things here. You won't get 1 minus epsilon. Yeah, you will not get 1 minus epsilon. Okay, other questions? I will not prove it. It's a calculation. You have to compute the size of this, put all the parameters, hope that things work. In the paper they say things work. I didn't check. I think it works. Not a very interesting calculation. Okay. Questions so far? Okay. So now let's prove the third part. So I'll erase this. If you have questions, yeah. They say this in weddings, in movies, right? You either object now or you keep your silence forever. So if you have questions, now is a good time to ask. So what is the setup now? So the setup is we have a queue of x, y, z. So x, y naught up to y, s. And it's 1 comma n minus 1, n minus 2, n minus s minus 1 degree is like epsilon p. This is a succinct way of writing what we just did. That its degree is this if you weight the ith y, the x variable by 1 and the ith y variable by n minus I plus 1. Okay, and we have that for all f in list of w, q of x comma f of x comma first derivative and so on. This is 0. This is what we have so far. What we will prove is the following claim, and this will imply what we intended to prove. We will prove that the list of W is at most the size of W divided by 1 minus epsilon p. For W being 1 minus epsilon pk, this gives you what you want. But this is what we'll prove. This is why I said the proof will not use the fact that W is equal to that. And in fact, we'll prove this bound by, there will be some induction involved, which there are a couple of ways of inducting on things. I will be a little hand wavy about that, but we'll see. So this is what we want to prove, and this implies the main theorem that we intended to prove. So how do we get our hands on that? How many polynomials are there, can there be, such that this can happen? So let's take some examples. So suppose that q was not an s plus 2 variate polynomial, but there was exactly one y variable. So if you are just looking at q of x comma y naught, and we want to understand how many f's are there such that q of x comma f is 0. F is a polynomial of some degree in x. How many such f's are there? How many f's can be there so that q of x comma f is 0? Q was not 0 to start with. Q was not 0, but when we went and replaced the y variable by a polynomial of degree n minus 1, it became 0. How many such f's can be there? Yeah, so the number of such f's is upper bounded by the degree in y of q. Why is that? You can just think of this as a univariate polynomial in y. Think of the variable x as being a part of the field. And what you're doing is you're plugging in different field elements for the variable y and you're getting 0. But this was a non-zero polynomial, so the number of roots it can have is upper bounded by the degree of the polynomial, which is the y degree of q. So this is upper bounded by the y degree of q. But the moment you let there be more than one y variable, so if you look at q of x comma y naught comma y1, this is non-zero, and you have q of x comma f of x comma f, first derivative of f. How many such f's are there? Like, is there a natural generalization of the above thing that will work here? This is now a differential equation, right? It's a differential equation of the first order, potentially high degree. So you're asking how many solutions can be there which are polynomials of low degree.
All I understood was that you will get maybe some d or like t evaluations of f which are equal to certain values.
You mean this part?
Yes.
Good. So the way to think about this is that instead of thinking of Q as a bivariate in X and Y, start thinking of Q of XY as a univariate in Y, where the coefficients come from the field of rational functions in X. So now it's a univariate polynomial. You're plugging in f of x's, which are just field elements. And you're asking how many field elements are there such that when I plug it into the polynomial, you get 0. That will be upper bounded by the degree of this univariate, which is the same as the degree in y of the bivariate. So the answer becomes more complicated once you don't have a single y variable, but you have multiple y variables and you are doing this differential equation thing. And this is what makes this proof tricky. The other thing is that we need a very precise bound, so that also makes life harder. The other thing the other thing to notice is that in this bound, whatever this bound came about, it didn't use the fact that f was in some list, right? This is the number of such f's is upper bounded by the degree in y of q, period. So we will use, in order to prove this, we will use the fact that f is in the list, w is a set which is not too large, and some of this should be obvious from the way the claim is stated. We are going to upper bound this list in terms of the size of w. Okay. Right, but we will again use it for this. To get this bound, we will again use it. Right, okay, so here's a theorem that will help us prove this bound. I don't know if we will have time to prove this theorem, but we'll prove the bound using the theorem. Then this is an independently nice theorem, exists independent of this paper. Sure. Yeah, no promises on if you will be able to read it or not, because I won't be able to read it 3 days from now, the way I write things. So, okay, so here's a theorem that's independently nice, and it will let us prove that. So if f in fp adjoin x comma q of xy comma alpha beta fp to the s plus 2 are such that so alpha comma f of alpha comma f1 of alpha s of alpha, this is equal to alpha beta. You should start seeing the similarities with the setup that we have. Q of x comma f of x comma f1 of x fs of x is 0. And third condition, write this in red, is that non-zero. So then, given alpha beta and q, f can be uniquely recovered. Okay, not the best way of writing this, but it will communicate. Let's parse it, and it will communicate to us what the setting we are in. So let's see what the hypothesis of this theorem is saying in terms of the graph that we constructed. So the graph that we constructed, there is some set W, there is a list of W, Okay, and alpha beta is a point in W. This condition, the first condition, is saying that there is an F here such that this edge is there. The first condition is saying that alpha beta has a neighbor, is a neighbor of F. The second condition is telling us that F is in the list. So Q becomes identically 0 when you replace the variable yi by the ith derivative. What's the third condition telling us? The third condition is telling us that so it's some condition about the derivative of Q with respect to ys. Q, because of the way we interpolated Q vanishes when you plug in x to be alpha and yi to be beta I. But the derivative of Q with respect to ys does not vanish when you plug in x equals alpha and yi to be beta I. Ys was the last y variable. You are taking derivative with respect to the last y variable. So that's what this condition is saying. And then the theorem is basically telling us that, so notice that this is a property of the point. This third condition is a property of the point. This third condition is telling us that this point is a non-degenerate 0 of Q. It's telling you that Q of alpha beta is 0, but dq over dys at alpha beta is non-zero. So if that condition holds and alpha beta is a neighbor of F, then you can use a non-degenerate point and the polynomial Q to uniquely go back to F. So in the picture, if you look at non-degenerate points, non-degeneracy is this condition. So if you look at non-degenerate points in W, let's call this subset W1. What this theorem is telling you is that all of these guys have a unique neighbor going out. There are no two neighbors. Because given this point and Q, you find the unique F such that this edge goes. So in some sense, non-degenerate points are great for us. These are points that have a unique neighbor on the left. Okay, so let's define this set. So let's define W1 to be alpha beta in W such that Q by dys at alpha beta is non-zero. And this theorem is telling us something about the graph on these points. If you pick points in W1, in list of W, they have a unique neighbor. They may have other neighbors elsewhere, but in list of W, they have a unique neighbor. Our goal was to find the size of the list of W. W1 is great for us. W1 is telling us that it's telling us that the part of the list that W1 sees, we have a good handle on it somehow. So the way we are going to prove that is essentially some kind of induction. We will use this theorem to recover what we can from the list by looking at W1, and then we will we'll somehow reduce it to a smaller case of the same problem of bounding the list of W where we'll apply induction. Okay, so now we have a choice to make. I am not going to be able to prove this theorem in time. So let's prove the list size bound using this theorem. Okay, so W1 is this. What is W2? Let's define W2 to be W minus W1. So this is W1 and this is W2. What do we know about W2? By definition, we know something about W2. Right. W2 is the subset of W where this guy, the derivative of Q with respect to ys vanishes on all points in W2, right? So dq over dys, so the observation is that this satisfies the interpolation constraints on W2. Right? What were the interpolation constraints? We had a set W. We wanted to find a polynomial Q with some degree constraint such that it vanished on every point in that set. this polynomial satisfies the exact same constraints on W2. Okay, so in the interpolation step, when we found ourselves a polynomial Q, instead of just taking any non-zero polynomial Q, let's find the minimal degree non-zero polynomial Q that satisfies the properties we wanted. If we had taken Q to be minimal, then this would immediately tell us that the set W1 is non-empty, right? So if Q was the lowest degree polynomial that satisfies the interpolation constraints, then the set W1 better be non-empty, because if the set W1 was empty, then this polynomial, whose degree is strictly smaller than the degree of Q, is also satisfying the interpolation constraints. So it contradicts minimality. So in the interpolation step, we should have said, let's pick the minimal Q that and work with that. Okay. So we are anyway doing this proof upside down. So pick the minimal Q, proceed, and at this point you realize that it will give us a non-trivial set W1 and a non-trivial partition of W into W1 and W2. W2 is strictly smaller than W1, and we would like to decompose the list of W in terms of list of W2. And, yeah. No, it need not be. I mean, as long as W1 is non-empty, this constraint doesn't contradict the minimality of, right? It's not vanishing on all of W, it's vanishing on some subset of W, which might very well be the case. Good, so that's the setup. So we will induct on W2. Okay, but we have to understand what is happening with the list here. So here's one observation. Let's call this claim 2. This claim 1. So if F in the list of W has at least, let's say, has one neighbor in W1, then it has at least P minus epsilon P neighbors in W1. So this picture is very lopsided. It's so the list of W can also be partitioned into two parts. There are polynomials here that see somebody in W1 and there are polynomials here whose entire neighborhood is contained inside W2. So they see nobody here. So there are, so these are, use some colors. So these are vertices whose entire neighborhood is contained inside here, inside W2. So these are polynomials that are actually contained in list of W2. And then there are polynomials that have at least one neighbor here. And this claim is telling us that if you have one neighbor here, you have many neighbors here. And this theorem is telling us that we can use any of these edges to recover the polynomial. We can start from any vertex in W1 and recover the unique neighbor in the list of W that is adjacent to it. But this claim here is telling us that, I mean, every guy here is going to be recovered many times, because you can take all of its P minus epsilon P neighbors and try to recover this. So you will recover it many times. So together they tell us that list of W, the size of the list I can upper bound it by, so it's at most list of W2. These are all polynomials whose entire neighborhood is contained inside W2. Plus, what are the remaining ones? The remaining ones are polynomials that have at least one neighbor in W1. But this claim, which we will prove immediately, tells us that you're not just going to get one neighbor in W1, you're going to get 1 minus epsilon fraction neighbors in W1. So the size of this plus the size of W1 divided by 1 minus epsilon P. Okay. Okay, now induction on this, if you induct on this claim on this, you replace this by size of W2 divided by 1 minus epsilon P. This is W1, W2 gives you partition of W, so the sum will be size of W by 1 minus epsilon. So that completes the argument. So things missing are this claim and this theorem. The theorem I am not going to prove, we don't have time for it. The claim is easy to show, I'll talk about this. Questions? So there's some induction built into this part of the proof. Okay, so should I erase? Let me erase the top of this. Okay, and let's prove claim 2. It's easy to show, I think. So let's take something in the list. It has a neighbor in W1. It means that okay, so let's define R sub f hat of x. We take the derivative and replace the variable yi by various fi's. Good. Now f has a neighbor in W1. So there exists an alpha. So f has a neighbor in W1. This means that there is an alpha in Fp such that Rf hat of alpha is non-zero, which in particular means that Rf hat must be a non-zero polynomial. As a polynomial, it's non-zero. Moreover, its degree is no more than the degree of Rf that we had constructed earlier, which was epsilon p, which means that there exist p minus epsilon p values alpha in Fp such that Rf hat of alpha is non-zero. But every such alpha is going to give us an edge from F that goes in W1. So that proves this claim. Okay, that theorem we didn't prove. That theorem is not, yeah, it's something that has been classically known and used zillion times. This paper, the proof in the paper is another application of that. It's not hard to prove.
But why do we differentiate with respect to y as we can't pick some
Right.
other variable?
No. Why? The degrees of Fi's is decreasing. That's what makes Ys special. And these theorems are proved using these power series based ideas. And yeah, Ys is special. Okay, but that's it. I mean, the last thing got a bit rushed, but if you have questions, I'm happy to.